Welcome to This Explainer. If you've got a high school chemistry exam looming on the horizon, well, you're in the exact right place. We're running a high-energy, quick-fire review of atomic structure and the periodic table to get you completely prepped. We are going to crack the atomic code together, moving from the tiny, microscopic center of an atom all the way out to the macro trends that basically define the entire world around us. So let's get right into it.
All right, here's our roadmap. We are starting at the nucleus with the core particles, zooming out to energy levels and those complex orbitals, spotting the pattern for the first 20 elements, and then applying all of that to figure out chemical reactivity and how to actually decode the periodic table.
Section 1, the core subatomic particles, the atom's population. We are kicking things off by looking right into the absolute center of the atom at our fundamental building blocks.
Okay, watch out for this because it's a classic trick question your teachers absolutely love to throw at you. An element's identity is strictly defined by its protons, period. Carbon is carbon because it has exactly 6 protons. But if you vary the number of neutrons, you just create different, slightly heavier or lighter versions of that exact same element. We call those variations isotopes. They behave exactly the same chemically, but they have a different mass just because of those extra neutrons.
Now here's the baseline math you are pretty much guaranteed to need on your test. Your atomic number is basically your master key. It instantly tells you the number of protons. And if it's a neutral atom, it also gives you the number of electrons. To find the neutrons, super easy. You just take the total atomic mass and subtract that atomic number. For instance, look at helium. An atomic number of 2 means 2 protons and 2 electrons. Since it has a mass of about 4, you just subtract those 2 protons and boom, you're left with 2 neutrons. It is simple, predictable math every single time.
Moving right along to Section 2, electron energy levels explained, the neighborhood's LETs. Let's look at where these electrons actually live, often labeled as K, L, M, and N.
Electrons don't just float around randomly. They follow the Bohr-Bury scheme. Think of it like building a hotel from the ground floor up. Each floor holds a very specific mathematical limit of guests based on the formula 2n squared, where n is just the shell number. So the first shell holds 2, the second holds 8, the third can theoretically hold 18. But here's the catch. You have to completely fill the inner shells before you start putting electrons into the higher outer ones. And for maximum stability, that very outermost shell loves to cap out at 8 electrons.
Take a look at potassium here. With an atomic number of 19, you've got 19 electrons to place. Notice how they are locked into these specific concentric rings around the nucleus. The first ring has 2, the second has 8, the third has 8, and there's just one single electron left over, hanging out in that fourth outer shell.
Section 3, understanding orbital types, the houses and rooms. Let's zoom in even closer on those energy levels, because this is where things get really interesting.
So forget those flat 2D rings for a second. Reality is way more complex. Electrons actually exist in these wild, three-dimensional clouds of probability. In the first shell, you just have a simple, spherical s orbital. But as you move out, you get these 3D dumbbell-shaped p orbitals sitting at right angles to each other. Go even further out, and you hit the highly complex d and f orbitals, which, let's be honest, kind of look like balloon animals made by a really confused clown.
Now, how do electrons actually choose which rooms to take? You've got to memorize these 3 golden rules. First, the off-bow principle. Electrons are fundamentally lazy. They fill the lowest energy orbitals closest to the nucleus first. Second, the Pauli exclusion principle. Any single orbital room holds a maximum of exactly 2 electrons, and they literally have to spin in opposite directions. And finally, Hund's rule. Think of this like strangers getting on a bus. People will always take an empty seat first before they reluctantly sit next to someone else, right? Well, electrons do the exact same thing in orbitals.
Section 4, the first 20 elements, the predictable pattern. Let's take those rules and apply them to the elements you'll definitely be tested on.
Honestly, do yourself a favor. Instead of memorizing 20 completely random complex configurations, just memorize the 2-8-8 rule for those first 3 levels. Your first shell caps at 2, your second caps at 8, and your third, for the purposes of these first 20 elements, fills nicely at 8. When a shell is totally full, like helium with 2 or argon with a perfect outer shell of 8, that element becomes incredibly stable. It has basically reached atomic nirvana.
Which brings us perfectly to Section 5, valence electrons and reactivity, chemical behavior. Why do we care so much about these specific shell counts? Because the outermost electrons, the valence electrons, completely dictate an element's chemical personality.
Let's look at our friend potassium again. Remember that 2881 setup? That single lonely valence electron in the fourth shell makes potassium incredibly unstable and highly reactive. It desperately wants to get rid of that one electron so it can drop back down to a perfectly full, stable third shell. Because of this, if potassium ever touches water, it throws that electron away so aggressively that it literally produces a violent explosive reaction.
See, it's all just a massive game of stability. Atoms will violently react, bond, share, steal, or give away electrons just to empty or fill a partially full outer shell. Elements like sodium want to lose one. Chlorine desperately wants to steal one. But on the flip side, look at the inert elements, the noble gases. Neon and argon have perfectly full valence shells, so they are totally chill. They literally refuse to react with anything because, chemically speaking, they're already perfect.
Section 6. Decoding the periodic table, the city map. Now we're going to zoom all the way out to see the big picture.
The periodic table is not just a random list of stuff, it's a meticulously organized city map. Notice how the columns, or groups, are organized strictly by the number of valence electrons. Group I on the far left, they all have one valence electron, which is why lithium, sodium, and potassium all react so vigorously. Skip over to group 7, the halogens. They all have 7 valence electrons and are super reactive because they just need one more to be full. And group 8 on the far right, those are your perfectly stable noble gases. Position literally dictates personality.
Okay, huge exam tip right here. Pay attention, because this trips up students all the time. Atomic radius trends. It makes total sense that an atom gets larger as you go down a group because you're physically adding more electron layers or shells further out. But shockingly, the atom actually shrinks as you move left to right across a period. Why? Because you're adding more protons to the nucleus without adding new shells. That increasing positive charge acts like a stronger and stronger magnet, pulling that outer ring of electrons tighter and closer in.
And that physical size directly impacts electronegativity, which is an atom's ability to pull bonding electrons toward itself. Electronegativity goes down as you move down a group. Why? Because the atom is just physically bigger. The outer electrons are further away, and the inner electron shells act like a shield, literally blocking the magnetic pull of the protons. We call that the screening effect. Conversely, electronegativity increases as you move left to right, because the atoms are smaller, meaning that powerful nuclear charge can easily grab onto nearby electrons. So to wrap this up, I want to leave you with a final, active, problem-solving question to chew on for your exam. Imagine you're a scientist who just discovered a brand new element. Based on its electrons, it's placed directly beneath potassium in group 1. How violently would you expect it to react with water? Think about how these patterns compound. It's further down, so the atomic radius is even larger. The screening effect is massive. That nucleus has almost zero hold on that single valent electron. If potassium is explosive, well, this new element would be absolutely catastrophic. Keep that kind of cause and effect mindset ready for test day. You understand the fundamental code of the periodic table now, so go out there and ace that exam.